We're talking about examples of linear transformations. And in particular, we're talking about linear operators, right? And linear operators are transformations that take a vector in one space and map it to the same space. So that's when the dimensions of the domain and the codomain are the same. So we talked about reflection operators, right? We talked about reflection, projections, and rotations. And that's where we left off on last time. So we're going to continue with the idea of linear operators. If you saw the examples from last time, they were all in two-dimensional space in R2. So now I want to talk a little bit about R3, linear operators in R3. So this may require a bit more visualization from our end to try to figure out what these operators do. So the first of its kind are reflection. We talked about reflection operators already, but again, we're talking about them in R3 now. So the kind of operator that we have, so we're going to have a similar diagram table. So we're going to talk about the operator. We're going to talk about the geometric application of it or visualization of the operation. And then we're going to talk about the standard matrix. And we like using T sub A to indicate that it's a operator called T with an associated matrix called A. Okay, so the first of its kind is a reflection about the XY plane. Now I'm dealing with a point in space, in three-dimensional space, right? So we have X, Y, Z. And we want to reflect this point, X, Y, Z, through the plane, the XY plane. So this may take a little bit more from out of us to try to see what that means. So we have the X plane, the X axis. We have the Y axis. Normally we would see the Y axis vertically, but in this three-dimensional space, we usually have X coming out in a diagonal like this, and then the Y is to the right, and then Z is above, right? And just recall, I don't know if you guys know about this, but recall the right-hand rule. Do you guys know about this, the right-hand rule?
Sounds familiar, but it's been a while.
Yeah, it's like, it's kind of hard to see this, but in the three-dimensional space, and if you take physics, especially in physics, you hear about this a lot, the right-hand rule or like the way things curl, right? So we use our right hand. The x-axis, use your thumb for the x-axis. The y-axis is your pointer finger, and Z is your middle finger. So if you were to extend your fingers out in this fashion, of course, you're looking at it from the other perspective, so you don't see what I'm saying, but this is the way we're going to visualize our axes, right? It obeys what's called the right hand rule, X, Y, Z. So X is the thumb, right? The thumb. This is the pointer finger. And this is the middle one, okay? That's normally like the way we visualize three-dimensional space. Okay, so yeah, just to answer the question. So the first exam, I said it was going to be the 6th, right? October 6th. But given the way things are going right now, we're not sure about when we're going back into class. So I think the best bet would be not next week, but the week after. So Wednesday, whatever 2 weeks from today is, it's after Columbus Day or Indigenous Peoples Day. Okay, just to keep you guys, and it most likely will be online because of the fact that we're not cleared yet to go in on campus yet. So at least the first exam will be online. Hopefully the next exam will not be online. Okay, we'll talk more about that next time. All right, so this is the XYZ, right? Now let's say I have, and again, this is not going to be so easy all the time to visualize, but let's see. Drawing this is definitely, so let's say I have this point here, this vector XYZ, and I want to reflect this through the XY plane. So you have to think about the XY plane as like a sheet, right? A sheet of paper, an infinite sheet of paper. So I don't know if you guys can visualize that blue parallelogram that I drew is a representation of the XY plane. And I'm gonna reflect this through, right? So you see this, I'm gonna have a reflection through it. Sorry, it doesn't look like a reflection. So then what would be the reflected, what would be the coordinates of that reflection across the XY plane?
Would it be X, Y, negative Z?
That's right. It will be X, comma, Y, comma, negative Z. So when I reflect this point here through this XY plane, the only thing that's being negated is the Z coordinate. Everything else stays the same. Does everyone see that? So then what would be the standard matrix? Well, remember how we find the standard matrix? We use our standard basis vectors. In this case, we don't have 2 standard basis vectors, as in the case of R2, we have 3 instead. So our standard basis, I just want to make sure everyone understands that the standard basis vectors in R3, we have E1, we have E2, and we have E3. And of course, these are 1, 0, 0, 0, 1, 0, and 0, 0, 1. Right? So then I want to figure out what is the image of each. So if I plug in T of E1, what happens when I reflect the E1 is right here, right? Somewhere here. This is E1. What happens when I reflect this vector through the XY plane? Don't I get the same thing back? So I get 1, 0, 0 because only the Z axis, only the Z coordinate is negated and everything else is stay the same. So if 1, 0, 0, if you negate 0, you get 0. So that's the first column, right? First column of A. And then T of E2. What happens when I bring the second basis vector through the XY plane, right? They're both, so you see how both of these are on the XY plane. So when I reflect it through the XY plane, I get the same thing again. Hopefully that makes sense. So this is 0, 1, 0. This is the second column. Of our associated matrix. And then finally, T of E3, that's this unit vector here. So when I reflect that through the XY axis, I do get something different. I get now it being a -1 for the Z axis. So then what's going to be my associated matrix to the operator T, which is a reflection about the XY plane, I would have this 1, 0, 0, 0, 1, 0, 0, 0, negative 1. So this is my reflection matrix through in the R3 in R3 that reflects my vectors through the XY plane. And then of course this is extended, correct? This idea is extended because what's so special about the XY plane? Why not the YZ plane? Why not the XZ plane? But by symmetry, I hope you guys see that they kind of should follow the same idea, right? So this is a reflection about the YZ plane. So what is the reflection about the YZ plane? So the YZ plane now is this one, right? It's this sheet here. And I have a vector. I drew it this way, right? Yeah, I have the vector somewhere. Again, this is difficult to draw on a two-dimensional surface. Yeah, XY, you draw it like this. So I'm reflecting this vector here across this YZ plane. So what's the only coordinate that's going to be affected if you reflect it across the YZ plane? Can anyone see that? So on the Y and the XY plane, the only thing that's affected is the Z coordinate. On the YZ plane, reflection across the YZ plane, the only thing that's affected is the
X coordinate.
X coordinate. So that's going to be reflected. So that will be, instead of XYZ, it's going to be negative XYZ. And again, drawing this is not the easiest thing. It's not the easiest thing. So this will be the reflection here of negative XYZ. So then what's going to be T of E1? Well, that's going to be the only thing that's affected, right? Negative 1, 0, 0. T of E2. T of E2 is on the YZ plane. So when you reflect it through the YZ plane, it stays exactly the same. And the same thing goes for E3. It's on it. So when you reflect it through it, that plane, it doesn't really affect it. So the associated matrix would be negative 1, 0, 0, 0, 1, 0, 0, 0, 1. So if you noticed, it looks very similar to the previous matrix, right? So they're basically just diagonal matrices with all ones across the diagonal, and except for one of them being a negative one. That's all the difference among these reflection operators. So the last one of these is the reflection about, so if we did the XY plane, we've done the YZ plane, then the last one, the only other plane that we have here is the XZ plane. So then we take our coordinate XYZ and we only have to worry about the Y coordinate. And we should already know what to expect with this, right? We should know that this is TE1. It's on the XZ plane. So I'm left with 1, 0, 0. It's unchanged. TE2, this is not on the XZ plane. And this is the one that's being changed to 0, -1. 0, -1, 0. I should probably move this down. And then lastly, T of E3 is 0, 0, 1. That's unchanged as well. And so the matrix here is 1, 0, 0, 0, -1, 0, and 0, 0, 1. Okay. And of course, in my attempt to represent this geometrically, call this X, call this Y, call this Z. And now I'm considering the XZ plane. And the XZ plane is something that looks like this guy here. That's the XZ plane that I'm trying to reflect the vector about. So if I have something like over here, this vector here, X, Y, Z, and I reflect it through it, I should get something on the other side, right? That's just a reflection. The other side of this. So obviously, whatever y coordinate this had here, it would have to be negative that y coordinate. So this would be x negative y, z. Okay, so this is how the operators go when they're reflection operators in the R3 dimension, in the three-dimensional space of real numbers, which is R3. Does that make sense, guys? It's just an extension of what we saw in R2, right? R3. But the idea is that these matrices are diagonal. They have ones, and one of those entries is a -1. Okay, so now we've talked about reflection operators. Then the next one is projection operators. Of course, we're dealing with R3 now. So what kind of operator do we have? Yeah, it is hard. It is difficult. So there's one thing about learning mathematics is the level of visualization that you need. And this is really from a creative aspect, like it's almost artistic in a way, right? Being able to visualize or understand things that you don't have at your disposal. Like I don't have a three-dimensional representation of R3. You just have to understand it kind of with your own mind in a way, right? So it's not easy, but we try to make this work. So the next kind of thing, right, is when you project. So it's a projection onto the XY plane. And we use the word orthogonal projection, right? Orthogonal projection onto the XY plane. So it's kind of similar, right? From compared with the reflections that we're doing, we're applying it. So here we're reflecting through planes, the three planes that we have, the XY plane, the XZ plane, and the YZ plane. And here we're projecting onto the XY plane. So again, I have a position in space, XYZ, and I want to know what happens to it when I project that vector onto the XY plane. So if this is X, this is Y, this is Z. And I have some vector, some plane, X, the XY plane. And I have a vector somewhere. And I want to project it onto this plane. I want to project it orthogonally. So my new vector will be something on the XY plane. And this will be orthogonal, right? So then what would be the orthogonal projection of the XYZ of the vector with coordinates XYZ onto the XY plane?
XY0.
XY0, that's right. So we got XY0. The Z coordinates just become, all of them become 0 when you project it, right? It's like a shadow again. So this idea of the shadow, right? We have a light source above and we project it onto directly above in an orthogonal fashion to the XY plane. So then what would be the standard matrix for this? Well, when I project 1, 0, 1, 0, 0 on the XY plane, I get the same thing, don't I? I get 1, 0, 0. When I project E2 onto the XY plane, I get the exact same thing, 0, 1, 0. But what happens when I project the E3? When I project E3 is the one on the x-axis, right? When I project the vector on the x-axis, on the z-axis, pardon me, onto the xy plane, what happens to that vector? All zeros, that's right, 0, 0, 0. So then what's going to be my associated matrix to this? This would be 1, 0, 0. This would be 0, 1, 0, and then 0, 0, 0. I'm going to use P for this, for projection matrix. So this is a projection matrix onto the XY plane. So every single time you apply a vector to this matrix, the last column is a bunch of zeros. And then you should start to see the relationship between the standard matrix and the projection, depending upon where you project onto what plane. So if you project it on the XY plane, all the Z's go away. If you project it onto the YZ plane, all the X's go away. And if you project it onto the XZ plane, all the Y's go away. So you're going to have projection matrices that look like identity matrices, but where one of those columns are all zeros. Does that make sense? I hope so. So another thing, so another thing is there's a lot of patterns, right? That you have to visualize and be able to come up with. So we have orthogonal projection onto the YZ plane. So again, onto the YZ plane, that means that all the X coordinates become zeros. And so the standard matrix for this guy would be, the first column would be zeros and everything else would be looking just like just like the identity. And what would that look like? So the YZ plane, right? So this is like my mirror now, and then I have a vector somewhere. And then I have another vector on the other side, and they're reflected. And no, it's on the actual, it's kind of hard to make this work, right? So the aspect of this is kind of difficult, but the idea is that this is projected onto projected onto it. So this is x, sorry, this is 0, y, z, and this is the x, y, z coordinate. Again, this is not the best manner. If only I could like rotate this, if only this app had a three-dimensional engine, right, where I can just like rotate this, but I can't. So maybe next time, maybe 2 years from now, 3 years from now, someone is able to figure out how to code or create a program that does that. Of royalty-free image. Could be. I could be able to do that. So orthogonal projection onto the last one, right? Onto the XZ plane. So T of X, Y, Z equals X comma 0 comma Z. We should know what this is going to appear like. 1, 0, 0. Zeros along the second column, which represents the Y axis. And this is 0, 0, 1. And you think this is hard to visualize? Wait until we do rotation matrices. Now that's gonna be quite fun, I think. Okay, so then we have so the XZ plane. Yeah, I guess this is just a way to show you guys how bad my drawing is. Because there's some people that actually can make this work, but there's like you need more of an artistic skill for that. So we have some vector in space, x, y, z, and then we project this along the xz plane. And so this would be x comma 0 comma z. Something to that effect. So these are the projection matrices onto the different planes that we have in the R3 space. And as you can tell, they look like identity matrices, except for one of the columns being all zeros. So if you have a projection matrix like this, where it's zeros along the third column, then you're projecting onto the XY plane. If you have a column of all zeros along the first column, then you're projecting it onto the YZ plane, and so on and so forth. Supposed to be a slice. Yes, Leonardo, yes. The blue square, I know, in my limited way of saying that this is the plane that we're projecting it onto. And yeah, and they do talk about planes. So like, yeah, we can head into this whole, like, we can head into a whole discussion about how do you teach mathematics for real? Like, how do you do that? People till this day are still trying to figure that out. Like, they're trying to figure out what's the best way, especially as how, you know, society changes, our circumstances change, careers become different, right? Like, how do you teach mathematics in this day and age? And so a lot of our textbooks are very antiquated. Like the style, the procedure, the way in which it's taught, it's an antiquated version of it. So they do teach about planes, but then how do you tell somebody, oh, wait, so this stuff is cool when you look at it from the perspective of linear algebra. They have to talk about linear algebra to ninth graders. How do you do that? You know what I mean? So it's kind of hard to know where to go first sometimes. Like, do we teach just the regular stuff first, the planes, just the way it is first, and then work their way up? So it's kind of hard to sometimes know what's best for the students as well, because some people teach differently. Students learn at different paces. They think differently. So that's another thing we have to worry about as educators. But in any case, I hope you guys see the connections that exist. You see, like when you talk about linear algebra, you may just think in the beginning, oh, we're learning how to solve systems of equations. Great. But then all of a sudden, we just make a turn and see more of a geometric reality behind these matrices. So then things start to become much more interesting because of the connections that can be made. So here we have reflections, three-dimensional space. We have projection operators in three-dimensional space upon the different planes. And then we have rotation matrices. Now these aren't, I'll try my best for this stuff. Because again, you have to remember the right-hand rule, okay? So the first of its kind operator, again, we were able to rotate things in various ways, right? In two-dimensional space, we're rotating about a point, right? We're rotating a vector about the origin through an angle, theta. Now, in this particular realm, we're going to be rotating vectors around an axis. So the first of its kind is a rotation about the x-axis. So we definitely have to try to interpret this geometrically speaking. So again, I have a coordinate for my vector. And this stuff, the second part is the harder. This is the harder, like what do we put as a result of taking x, y, z and rotating it about the x-axis through an angle of theta. And of course, we're talking about a counterclockwise rotation, right? This is always counterclockwise. And that's where the right-hand rule comes into play. So again, x, y, z. And my x-axis becomes my axis of rotation. This is my axis of rotation. And so I have, and it's the positive x-axis, that's my axis of rotation. So it's this. Okay. And what if I have a vector? Whoops. Somewhere in space. X, Y, Z. And I want to take this vector and I want to rotate this. I want to rotate this about this axis of rotation by theta. Again, try our best to do this. And I get this new vector here. How do I interpret this? Well, again, we can look at the E1, E2, and E3 case, right? And with these cases, I think I can have a better understanding of what happens. So take E1. E1 is actually on the axis of rotation. E1 is 1, 0, 0. What happens when I take 1, 0, 0 and rotate it about the x-axis? What's going to happen? If I take a vector that's on the axis of rotation and I rotate this vector theta degrees about this axis of rotation, what would be the result?
Should stay the same.
It should stay the same, and it will, right? 1, 0, 0. So that's not the hard part. So if you're on the axis of rotation and you rotate about that axis, then you're still the same thing. You're still the same vector. Now, what happens when you're E2? Right? What happens when you're E2 now? What happens when I rotate this? So remember, we're rotating about an angle of theta degrees around the x-axis. So then I want to rotate this guy also theta, right? By theta, about the x-axis. So then what's the result of that? So how would you interpret that? So for those of you who took, any of you who took physics, we talk about like the magnetic plane and like, there's different ways, right? We can talk about certain things. So take the X, Y, Z space and rotate it in a way where you're looking directly at this arrow right here. This x-axis here is just pointing towards you now. Do you guys understand what I'm doing? And then this here is what? This is the y-axis and this is the z-axis. Do you guys see what I'm doing? And then E2 is right here. And I'm rotating this by theta. I think this just stopped working. Hold on. Let me do this again. Stop sharing. Okay, do you guys see that? Now, what would be the new coordinate of E2 if I rotate counterclockwise by theta? Do you guys see this? How like this x-axis in a way doesn't matter so much anymore? After you consider it as an axis of rotation, just think about the YZ plane now. Just think about the YZ plane and having that E2 guy being moved by theta. Do you see how now this is similar to what we did in the previous lecture with the rotation on the XY plane? Now the difference is now this is instead of X, it's Y, and the difference of this being Y, it's now Z. So what does that mean? What are the coordinates of this new person, this new vector? So E2, remember what's E2? It's 0, 1, 0, correct? Now, because I'm on the YZ plane still, my x-axis will, my still x coordinate will still be 0. So I know for a fact that the result will still be 0. But then what's going to be the y coordinate? Do you guys see how that, what that will be? Do you guys see how we can set up a right triangle again? Do you guys see how, since it's a rotation of a vector, the length of the vector doesn't change, so then my length will still be 1. Now, how do you figure out this height here of this triangle and this height here of this triangle if you know theta and if you know the hypotenuse is 1?
Is it radical 2?
Rad 2 would only be right if theta were 45 degrees.
Ah, right. Okay.
So we don't necessarily know what theta is. It's an arbitrary angle. But given that we were to know what theta would be, what would be the vertical side of that right triangle and the horizontal side of that right triangle using the fact that it's theta that we know theta, and using the fact that the hypotenuse is 1. Right? Something with trig comes up again, right? So now it's going to be sine. So which one is sine? Is it this one that's sine or this one that's sine? The opposite, the one standing up, right? So the one that's above here, this would be sine. And the one below would be cosine. But then how does that relate to the y and z coordinates? Which one is the y coordinate and which one is the z coordinate? Do you guys see that? Do you see how this is the z coordinate? This is the y coordinate now of my new vector. So this would be cosine theta sine theta. And this would be my new vector, cosine theta sine theta. Does that make sense, guys? So the E2 is being taken to the point 0, comma cosine theta, comma sine theta. Now do the same exact thing for E3. I'm rotating E3 by theta with respect to what? To the x-axis, right? So then what's going to happen? I'm going to rotate this in the counterclockwise direction. This is theta. And then I can do the same right triangle thing again. And I already know what this is, right? I already know what the right triangle would be. I know this would be sine. I know this would be cosine, correct? But now what is this new coordinate going to be? Again, this would be still 0. But then what's going to be the y coordinate? And what's going to be the z coordinate? Can anyone tell me?
Sine theta, then cosine theta.
So be careful. Now, this is the positive y-axis. This will be negative.
Gotcha.
So this should be now what? Negative
sine theta,
comma
cosine
theta, right? So that's going to be negative sine. So it's going to be what? 0, negative sine theta, cosine theta, correct? And so then what's going to be my reflection? So I'm going to use this. I'm going to use my rotation, pardon me. Rotation with respect to the x-axis. This would be 1, 0, 0, 0, cosine theta, sine theta, and 0, negative sine theta, cosine theta. And this is the rotation matrix about the x-axis. Do you see how we were able to figure out what would be the rotation matrix? So I figured out, yes, Baldwin.
Sorry, Professor, that was by accident.
Oh, that was by accident? Okay. So then what would be the, how would I define now my operator, my transformation? So take a vector somewhere, some vector, 1, 0, 0, 0, cosine theta, sine theta, 0, negative sine theta, cosine theta. Multiply it by x, y, z. What would be the result? I would have x, right? So x stays the same. Then the y coordinate would be what? Y cosine theta minus z sine theta. And then the z coordinate would be y sine theta plus z cosine theta. So that would be the coordinates of my image of my vector. If I rotate it by theta degrees about the x-axis. Any questions about this? Again, this is the hardest part of all of this. This is the hardest one because of the trying to visualize it, trying to see how this fits in with the rest of the operators. How do you get the operator itself? But any questions about this? Because the other ones follow the same format. It's the same idea. Sure, the matrices will look a bit different. And you should probably already start to wonder what would be the differences among the rotation matrices. Okay. Okay, so then the next one is rotation about the y-axis by an angle of theta, by an angle theta. So what happens when I take x, y, z and I rotate it about the y-axis? So now I'm rotating this about the y-axis. And I'm taking some point in space, x, y, z. Actually, let me do it this way. Yeah. So I have x, y, z, and I'm rotating this by theta about the y-axis. So I get something that's around it, right? It's like something it's like this is going around like this, right? This is going around in this fashion. So this vector here is rotating about the y-axis. I'm doing it by theta. So then what is it gonna look like? What's the matrix gonna look like when I do this? So then how do I visualize this? What should I do? I can't look at it from this perspective, right? That's kind of difficult to do. So then what I'm going to do is I'm going to do something very similar to what I did here. I took the x-axis, the positive x-axis, and I drew it in a way that it's coming out of the page, right? This is like it's coming out of the page. And so then if I were to look at it from that perspective, then the y-axis is to the right and z is above, right? The positive y-axis to the right and the positive z-axis is above. I'm going to do the same exact thing. I'm going to create an axis again. The center of it will be the y-axis, so popping out. So my y-axis now is popping out. So if the y were to be popping out, if I'm looking at it from this perspective here, if my eyes are looking at it from this perspective, then my positive axis for the x-axis would be to the left. Do you guys see that? And the positive axis here would be z. And that's where the right-hand rule applies. Do you guys see that? And so then if I have, so if I have E1, remember, we're always looking at E1, E2, and E3. So if I have E1 here, what happens when I rotate this vector E1 by theta degrees counterclockwise with respect to the positive y-axis? So this is theta. This is my new vector under this transformation. This is theta here. So then what would be my new coordinates? So if I'm on the XZ plane, right? This is on the XZ plane still. So the Y coordinate has to be 0. What matters is what's my X axis, what's my X coordinate, what's my Z coordinate. Again, this is 1, right? The length of this vector is 1. So this vector continues being 1, the length of it. Now I have a right triangle that I can use, given the angle theta, that can tell me what this side is and what this side is with respect to theta. So then what would be this horizontal component of this vector with respect to theta? It would be what? Cosine theta? Which sign is negative, which sign is positive? Well, that's exactly what I'm saying. So the way we draw the XY plane, right? The XYZ space, this is positive, positive, positive. Now I'm looking at the Y axis, at the positive Y axis. This is the positive Y axis. This is coming out of the page, right? So the positive, this is positive X axis. This is negative X axis. This would be the positive Z axis. This would be negative. So this is positive, right? This is positive. This is positive. So that's why I have this format here. So the X axis here will still be positive. But as you can tell by theta, right? If I rotate this by theta, my vertical component will be negative Z. So this will be negative sine theta. That's my new vector. This is TE1. I should write that. TE1. So TE1 is cosine theta, 0, negative sine theta. And then what happens with E2? What happens when I rotate E2, which is on the y-axis, and I rotate something that's on the y-axis about the y-axis? What's the result? E2 is unchanged, right? So this is 0, 1, 0. So that's expected, right? That's expected. And then lastly, it's the E2. What happens with E2? I mean E3, pardon me. E3. Zero, zero, one, right? I'm rotating it again by theta. So I'm rotating this by theta. So again, I have this right triangle that I can form. And by now, I should already know what's going to happen, right? The top here, this here is sine theta, and this here would be cosine theta. But now with respect to the xz coordinates, what would be the xz coordinate? So T of E3. So again, the y-axis, the y coordinate would be 0, but what would be the x coordinate? And what would be the y coordinate? I mean the z coordinate. This is positive x, right? So if it's positive x, then this would be positive sine. And what would be the z coordinate? What would be this part here, right? So this would be positive cosine. So then the result is sine theta 0 cosine theta. And so then what would be the rotation about the y-axis? It would be the matrix cosine theta 0 negative sine theta 0 1 0 sine theta 0 cosine theta. Is this clear, guys? Does this make all sense? Does this make sense at all as to what I'm doing with the viewing the axes in a certain way, so that I can tell how my standard basis vectors, how they're behaving under this transformation? And you see that once I know what E1, E2, E3 is, I can know what it does to any vector. That's the beauty behind this. So now if I apply the rotation matrix across about the y-axis to any vector, I know exactly what happens to it. So I get what? I get x cosine theta plus z sine theta. I get y, and then I get negative x sine theta plus z cosine theta. And so this would be my operator. This is how I would express it. So any questions about? It'll take some practice. Yes. Yes. Of course. So the last one, and then we'll be done with these kind of matrices. We'll be finished. We're trying to find out what they are. But I hope it makes sense. So this is now rotation about the z-axis through an angle of theta. Through an angle theta. So now in a way, right, we only care about the z-axis. We only care about the z-axis. So my z-axis now is my center of rotation, my axis of rotation, right? I'm rotating about the z-axis. So if I have a vector somewhere in space, x, y, z, I want to rotate this vector by theta until I get my new vector, right? That's the idea. So what does that look like? Well, let's apply it to our standard basis vectors and see what happens. But in order to do that, now I will do what? I'll visualize this as if I were looking straight, if my eyes were right here and I look straight into the z-axis. So when I do that, what happens? This is my z-axis that's coming out, right? And if that's coming out, I just have to be consistent with the axes. That's all it is about the right-hand rule thing, the 3 fingers. I just have to be consistent. So if this is a z-axis, and if I look at it from this perspective, right, I could write it this way. I could write that this is my x. If this is my x, then this has to be my y right here, positive. So I'm gonna write this is positive, positive, positive. So the positive x-axis is coming out of my page. So the positive x-axis would be going, if it goes to the left, then the one right beneath it should be positive y. So then how does that affect things? Well, then this would be E1, and this would be E2. And of course, E3 is on the z-axis. So if I apply the rotation on E3 on the z-axis, about the z-axis by theta, I'll get exactly the same vector. So I know that's going to be a fact. And if you notice for the rotation matrices, that always appears, right? It always appears that if you rotate about the x-axis, you forget just leave it as 1, 0, 0, E1. If you rotate it about the y-axis, then the second column will be 0, 1, 0, which represents E2. And then for the z-axis, it's the same idea. You get 0, 0, 1 for the third column. But what happens with the other columns, right? And this is again where we have to use the little bit of trig. So this would be theta. This would be theta. And so then we already know, right? We should already know what's going to happen. This here is cosine theta. This here is sine theta. This here is cosine theta. This here is sine theta. It's just that what's going to happen is the XY coordinates will change depending upon where I am and what quadrant I am in, right? So here, what's going to be the coordinates of this guy? Of TE1. Well, I know what Z is already, right? I already know this would be the Z coordinate will be 0. What's going to be the cosine sine, right? So positive or negative. So the x-axis here will be cosine. And the y coordinate will be sine because they're both positive. You see that? Positive here, positive here. I'm positive. So then this will be the first column. First column would be cosine theta, sine theta, 0. And then the second column would be what happens to E2 under the transformation. So what's going to be E2? Well, in the x-axis, it would be what? Negative sign, right? So we got negative sine theta. Then we got positive cosine theta and then 0. So this will be negative sine theta, cosine theta, 0. Okay. And so then we found the 3 rotation matrices with respect to their different axes. So this will be our z multiplied by any vector. I have cosine theta, sine theta 0, negative sine theta, cosine theta 0, and 0, 0, 1. Multiplied by some vector x, y, z. Oops. And when I do that, I get x cosine theta minus y sine theta. I get x sine theta plus y cosine theta, and then I just get z at the end. So that's the formula. Every time I rotate a vector in 3-dimensional space about the z-axis by an angle of theta. This is very powerful stuff, very powerful. And it becomes powerful when you realize that you can apply these transformations one after another in succession. So let's say you want to rotate in a much more specific way. You just don't want to rotate about the x-axis, nor about the y-axis, nor about the z-axis, but you want a combination of them. You want to rotate about the x, and then the y, then the z. Then what that entails is multiplying the matrices one after the other. Leonardo, you have a question? Isn't it cosine sine theta for the first row? are you talking about this one? Okay, so the idea is that when you, oh, I should have wrote this here. Sorry. When you find the image of E1, E2, and E3, the image, which we found, right, to be these coordinates are actually the columns of my new matrix. They're not the rows. So that's the idea behind finding the columns of the associated matrix, okay? So we utilize our standard basis vectors, and I know there's a little, there may be some confusion because you see them as rows, right? You see these numbers as rows, but really this coordinate here is what's called a comma delimited form. It's basically just an n tuple, a 3 tuple. So you have these commas, right? But you can write this as a row vector, or you can write them as a column vector. But normally, because we're associated a vector, a matrix with T, right? This is A multiplied by E1. And in order to do this, E1 has to be a column. So we get a column multiplied by a matrix, and we get another column vector. So that's why we have columns. And then these columns become the columns of my associated matrix. So that's why we're consistent with treating them as columns. Okay. Okay. Great. So now we've talked about the same thing we've spoken about last time, just now in 3-dimensional space. And I hope the biggest thing out of this, guys, the biggest thing out of this is that you're able to now see how important it is to understand where do the standard basis vectors, where do they go to? What is the image of the standard basis vectors under the given transformation? So that once you're able to figure out where each of those standard basis vectors go under the transformation, I can figure out what the matrix associated with that transformation is. And once I have that, I can apply that matrix to any other vector, since every other vector is a linear combination of those what are called standard basis vectors. So that's really the goal behind all of this. And because of that, the geometry behind this, you see, it would be very difficult, for example, with rotations, to understand what in the world does that mean to take a vector in random space and rotate it about the x-axis. It would be very hard if we were to just be given a random vector and rotate this vector about the x-axis. It's kind of like, wait, I don't even know where to start. But that's why when we broke it down with E1, E2, E3, it's actually a bit easier, right? So we're basically finding the components of the XYZ. We're just finding what the first component is. What happens with just the first component? What would happen if I just rotate the X component and then the Y component and then the Z component? And then when you put them all together, you get this very nice matrix, right? Okay, so then once we have this, then we can talk about composition. Composition of linear transformations. And this is where you should kind of think about, recall, I should say recall composition of functions. Remember this, guys? Remember when you had F followed by G? Who remembers what this denotes, what this means? Composition functions, right? So that's right. This means F of G of X, right? So what comes first? G is first, right? And then F is second. So it's like saying, right, it's like saying I got an input. I apply f to it first. The result is f of x. And I'm plugging this guy into another function called g, right? So this is f, this is g, and the result is f of g of x. And this is the output. So that's the idea behind composition of functions. Like an onion, that's right, Mahmoud, similar to that, right? Now, it's the same exact thing, but now I'm just applying transformations, which are pretty much just functions. So like if I have a transformation with a certain matrix associated with, followed by another transformation with another matrix associated with it, and I'm applying it to a vector, what is that going to look like? That's going to look like T of A, but I'm applying T of B first to V. But since there's a matrix associated with B with T, there's a matrix for this operator, and that associated matrix is B, I can also write this as the following. I can write this as A multiplied by B multiplied by V. So we'll see that in action. So this is a composition of linear transformations. So composition of linear transformations is similar to just saying multiply the matrices in this order. And also just be careful that the other way around is not necessarily the same, right? Composition of functions is not necessarily commutative. They're not necessarily commutative. So remember that A multiplied by B does not necessarily mean B multiplied by A, where A and B are matrices. This is an important fact about matrix multiplication. It's not commutative. So in other words, matrix multiplication is not commutative. Okay. Okay, so I'll give you an example. So let T be a transformation that takes R2 to R2. So my domain is R2 and my codomain is R2. So let T be a linear transformation that is a composition of transformations where first it reflects through the x-axis and then reflects through the line y equals x, y equals x. And then the question is find the standard matrix A of T. So how would I find that standard matrix? So first of all, what's the first transformation? My first transformation is reflecting across the x-axis. So I'm gonna call this T1, right? T1, reflecting across the x-axis. Now, what is the and I'm gonna call the associated matrix A1. Does anybody remember what is the matrix form of reflecting across the x-axis? Remember, we're in the 2 by 2 case. I'm reflecting across the x-axis. So then what does my matrix look like? We talked about this last class.
Going top to bottom, left to right, 1, 0, 0, -1.
That's right. So that's my first matrix, right? Associated with my first transformation. Then my second transformation that follows it is T2, and I reflect across the line y equals x. I'm gonna call that matrix associated with T2 A sub 2. So then what does that matrix look like? When you reflect across the line y equals x, you switch the x and the y's. And that matrix is what? So when you swap the x and the y's, remember this becomes 0, 1, right? And then 1, 0. So then when I want to find what is t, isn't T2 followed by T1? So if I want to take t and I want to apply it to some vector v, right? It's the same thing as saying T2 followed by T1 and taking v, right? Which means I'm taking T2, but first I'm applying T1 to it. But to get T1 of v, I'm really applying the matrix A1. And then I'm going to be applying A2. But because remember, matrix multiplication is associative, I can also write this as A2 times A1 first, and then V. Matrix multiplication is associative. So then what is A1 times A2 really? And remember, the order matters, right? So A2 is what? 0, 1, 0, 1, 0. And what's A1? 1, 0, 0, -1. So when I multiply this, what am I really saying? When I multiply this out, row 1, row 2. This is really 0, right? And then row 1, second column, -1. And then row 2, first column, get a 1. And then row 2, last column, I get a 0. So this is really my matrix. 0, 1, -1, 0, multiplied by V. That is T of V. And so this is my standard matrix A. Does that make sense? Instead of multiplying this matrix and then this matrix, I can just multiply this matrix, these two matrices together and create just one matrix. And this one matrix does exactly what it's expecting us to do. We reflect about the x-axis first, and then we reflect about the line y equals x. But if I just want to do that in one fell swoop without having to do the sequence of transformations, I just apply this matrix. And this matrix, when I multiply it by any vector to this matrix, I do exactly what was just being said. Reflection across the x-axis and a reflection across the line y equals x. So now we can treat these matrices as a sequence of matrices that are multiplied together, and that gives us a result, which that matrix at the end is the result of applying those several, more than one transformation in succession. Does that make sense? So the composition of functions that you learned about when you learned about composition of functions is still being applied to this case with transformations and matrices. Okay. Any questions, guys? Anything? Any comments? Are you guys okay with this so far? I hope so. I hope so. So far, so good. Okay. Now, with that in mind, we're going to talk about invertibility. So again, this whole idea of invertibility pops up again. Sam, do you have a question?
Yeah, I was just wondering if we have a chance, if we have the time, could we do an example that's maybe a little more complex? I don't know, maybe like one of the R3 transformations, R3 to R3.
You want to do that?
I mean, I think it would be helpful.
I mean, yeah, it really just boils down to multiplying 3 by 3 matrices.
Oh, it's
So
really no different then. It's just, yeah, just a larger amount of
it's just a
data.
larger, yeah, it's just a larger, it's more computation. And of course, it's more interesting though. It is. This is a simple example, right? The reflection across reflections across lines in two-dimensional space, not that interesting. What gets interesting is what I was saying before, right? Let's say you want to rotate a vector about the x-axis and then do the same thing, like rotate the matrix about 45 degrees, a 45-degree angle about the x-axis. And then you want to rotate the same vector again by around the z-axis by 60 degrees. So then I can just run you through that. So what would that look like? What would that look like?
A lot of trig functions.
Yeah, so just a simple example, right? So find the standard matrix of a transformation which is a composition of a rotation about the x-axis by pi/3 radians, followed by a rotation about the z-axis by 45 degrees. So I'm using radians, I'm using degrees, and my screen is frozen. Oh, you got it, right? Okay. Okay, so then I'm trying to find what is t, right? When I apply v to it, what is that matrix A, right? That's what I'm looking for. But okay, what do I know about t? The transformation that I'm dealing with is a rotation about the x-axis followed by a rotation about the z-axis. And of course, this is going to be pi/3. So theta here is pi/3 and theta here is 45 degrees. So then you have to go back. What is the rotation matrix for r of x, right? It's 1, 0, 0. 0 is a cosine theta sine theta. 0 negative sine theta cosine theta, right? If my memory serves me correct, which it is, right? negative sine theta.
Wait, Professor, I think for the x-axis rotation, you put pi over 3, or am I remembering that wrong? Yeah, pi over 3 radians, 60
Yeah.
degrees.
Yes. Yes. So then when I apply the theta being, when theta is pi over 3 radians or 60 degrees, right? Now I actually have to plug that in.
Oh yeah, I misread. I thought you put 45 in that second theta spot in parentheses.
No, yeah. So this is cosine of pi over 3. This is sine of pi over 3. This is 0 of negative sine of pi over 3. And this is cosine of pi over 3. Which would be well, it would give me what? 1, 0, 0, right? This would be 0. Pi over 60 is 1/2. Sine of 60 is rad 3 over 2. 0, negative. This is negative rad 3 over 2 multiplied by 1/2. And do the same exact thing for RZ. RZ was what? Let me just copy this real quick. So this is RZ. And then I make the angle, I want the angle to be 45 degrees. So then my RZ rotation matrix becomes cosine of 45 degrees is rad 2 over 2. This is negative rad 2 over 2, rad 2 over 2, rad 2 over 2, 0, 0, 0, 0, 1. And then you have the task to find what A is, but A is really what? RZ multiplied by RX. And remember, RX is first, so it's on the right side, and then the left side is the second rotation matrix. So then you have rad 2 over 2, rad 2 over 2, 0, negative rad 2 over 2, rad 2 over 2, 0, 0, 0, 1. I'm multiplying this by 1, 0, 0, 0, 1/2 rad 3 over 2, 0, negative rad 3 over 2, 1/2. And I think you can take it from here, right? You can see what happens. First row, first row, first column, what do you get? You get rad 2 over 2, and then this becomes negative rad 2 over 4, and this becomes negative rad 6 over 4, and then this becomes rad 2 over 2, this becomes rad 2 over 4, and then this is negative rad 6 over 4 again, and then you get 0, you get rad 3 over 2, and then you get 1/2. And so this would be the matrix A. Do you see that?
Yeah.
So this matrix would be the matrix associated with the transformation that takes a vector, rotates it about the x-axis by 60 degrees, and then rotates it about the z-axis by 45 degrees. Instead of multiplying it individually with these two matrices, multiply these two matrices first, and then you get one matrix that does those two transformations at once.
Got it. Makes sense.
And that's the idea. And so then that becomes very, very useful, because then you can just play around with rotations and projections and reflections, that you can do a whole bunch of an assortment, an array of different sequences of transformations. And then it just entails multiplying matrices together. So you see, hopefully now you start to see, oh, when I'm multiplying matrices, sure, I'm just multiplying numbers and adding them up and putting it in the right order. And I can think of it that way, as just a purely computational task. Or I can think about it maybe, well, now that you know what these matrices look like, you can say, oh, this matrix is a rotation matrix followed by a projection matrix onto the XYZ on the XY plane, followed by a reflection across the the XZ plane. Like, you can now visualize these things when you have them, when you're able to identify this 3x3 matrix.
So given that standard matrix, that means now you can use that and multiply to any matrix that works with it, and you
Any
can get the
vector.
same
Right,
transformation.
right,
Okay.
right. That's the idea. So now the entries in this matrix, what's embedded, what's encoded in these numbers is exactly what we're saying in words. We're rotating about the x-axis with 60 degrees by 60 degrees counterclockwise, and then followed by a rotation about the z-axis by 45 degrees. That's embedded now in this matrix. Where if I just gave you this matrix, you would never be able to figure out, wait, where does the matrix come from? It's just a random matrix, right? It just seems random. But then now you have the information that's embedded in it, encoded in it. So that's the cool thing about linear transformations. Now you're treating them as a composition of them. You can apply one transformation and apply another, and apply another, and so on and so forth. And in that regard, we're going to talk about invertibility of linear transformations. In a sense, you've been learning about inverses the whole time you've been learning about mathematics. Because every single time we learn about how to do one thing, we also want to learn how can we undo it, right? When we learn about adding, we said, oh, we can undo adding by what? Subtracting. When we learn about multiplying, what else do we know? Oh, we can undo multiplication by division. When we exponentiate by 2, how can we undo exponentiation? We take the square root. So on and so forth, right? So the idea of inverses is, without using another word, embedded in mathematics. So if I apply a transformation, such as reflection, it kind of seems natural. I can undo the reflection, right? So if I reflect across the x-axis and R2, how do I get back the matrix that the vector that I started with? I just reflect it back. So then we're going to talk about invertibility. And then associated with invertibility is the invertibility of the matrices. So if the matrix that's associated with the transformation is not invertible, then the transformation is not invertible. And then if the matrix is invertible, then the linear transformation will be invertible. Okay, so that's the kind of idea. We're applying inverses now to transformations. Okay, so for example, let me give you a linear transformation, R2 to R2. And T is linear. T is a linear transformation. So I have to specify that, right? Because not all transformations are linear. I just want to make sure that's clear. You can have a transformation that's not linear. And remember what constitutes a linear transformation? Does anybody remember the properties? There's 2 of them, right? There's only 2 properties that every linear transformation has. Does anyone remember? No? These are very important properties. So remember, one of them is if you have an input that is a sum of 2 vectors and you're applying the transformation onto it, it's the same as taking the transformation to one of them and adding it to the transformation of the other. This is one characteristic of being linear. Like I said, not all transformations hold this property, have this property. And the other property is that if you have a vector and a scalar multiple of that vector, and you want to know what the image of the scalar multiple of a vector is, it's the same thing as finding the image of that vector without the scalar multiple and multiplying the scalar multiple afterwards. So if you have a transformation that makes these 2 things true, then it's linear. If one of these properties does not hold, then it's not linear. Does that make sense? So note, any transformation that does not abide by the two properties above is not linear. So that's important. And please don't worry about my dog. He hears stuff and starts barking. So pardon me for that. Does that make sense? So not all transformations are linear. Linear transformations have these two properties that are true. If you don't have these two properties being true, then it's not linear. If you do, if both of them are true, then it is linear. So I'll give you an example. T of xy is equal to 2x plus 7y, 8x plus 29y. So how can I represent this as a matrix? How can I represent T as a matrix? What is the standard matrix of T? You guys remember how we do that? How do we find that? 2, 7. 2, 7. So you're Leonardo, you're saying the rows, right? 2, 7, and then 8, 29. Is that what you're saying? Yes. Okay. Yes, that's right. So this is 2, 7, 8, 29. So when we say T of V, this is the same thing as saying 2, 8, 7, 29 multiplied by x, y, right? Now, that's the standard matrix representation of my operation, of my transformation T. And now the idea is I want to find, and I'm gonna call this, the result is I'm gonna call this, we'll call this U and V. Now find what is T inverse. So what do you think that entails? To find the inverse of T would be finding the inverse of what? Do you guys understand my question?
It's the inverse of that product, the inverse of UV.
It's not the inverse of UV. So yeah, maybe I should rewrite this, not UV. Sorry, let me use AB. So what's happening? What's happening? T, right, goes from R2 to R3 to R2. Where is this from? V is from this guy, and then AB, the matrix A, the vector AB. So I'm gonna write this as XY. XY is in R2, and then AB is in R2 as well. Now, what is the inverse gonna do? Remember, what is a property of inverses? It takes the codomain or the range, and that becomes my new domain. So again, the inverse takes something in R2 and puts it back to R2. But really what I'm trying to say is if given a vector AB, I want you to get back XY. Normally we're given XY, we apply A to it and we get AB. Now given AB, I want to find what do I have to do to AB to get back XY. Do you guys see that? So if A times V gives me AB, then what do I need to do to get AB by itself, or to get V by itself? What do I need to do to get XY by itself? What do I need to do to get this guy alone? I gotta get
Multiply the inverse of A.
I gotta find the inverse of A, right? So when I apply the inverse of A on both sides, what happens? I get xy by itself, and I get A inverse times AB. So in other words, the standard matrix of T inverse is equal to A inverse. That's all. That's literally all it is. So what is the inverse? If A is 2, 8, 7, 29, what would be the inverse? Well, how do you find the inverse again?
Switch A
One.
and B
Mhm.
and the determinant, yeah.
Right, so this becomes 29, 2, right? And this becomes -7, -8. So when you multiply AD minus BC, I get 29 multiplied by 2 minus 8 times 7. And that would be what, 58 minus 56, and I get 2. So this is equal to 1/2, right? 1/2 multiplied by 29, -8, -7, 2. If I multiply 1/2 everywhere, I get 29 over 2 minus 4 minus 7/2 times 1. This would be A inverse. And A inverse is associated with the inverse transformation, T inverse. So what is T inverse going to look like now? So T inverse is when you multiply, right, by AB, for example. This would be the same thing as saying A inverse multiplied by AB, which would be the same thing as saying 29 over 2, -4, -7/2, 1. And I multiply that by AB, which results in what? 29 over 2A minus 7/2 B, -4A plus B. That's what T inverse does. Or if you want to rewrite this, you can rewrite this as the following. Now this AB stuff, at the end of the day, doesn't really matter. I can write them with any other variables. So I just care about what T inverse does. T inverse does what? Takes the first coordinate, multiplies it by 29, subtracts it by 7/2 of the second coordinate, and then so on and so forth. The first coordinate multiplied by -4, and you add by the second coordinate. So in reality, I can write it as this as well. X comma y is equal to 29 halves x minus 7 halves y, comma, -4x plus y. So this is the rule for the inverse of t. I gave you the rule for the regular just t, right? T is the rule given by this. If I give you x and a y, this is the result. This is the image. I was able to find the inverse, the standard matrix of that transformation. And I wanted to find the inverse of that transformation, which entailed just finding the inverse of the matrix A. And that's pretty straightforward to do if you know the formula for the inverse of a 2x2 matrix. And once I have that 2x2 matrix, the inverse, then I apply it. I apply it to some random vector. And whatever that random vector is would give me the inverse of whatever t would be. And then I can rewrite the rule for t inverse and these with using these coordinates. So again, the inverse of a transformation is simply the inverse of the matrix associated with the original transformation T. Any questions about that? No questions. Okay, since no questions, let's see if we can do one more of these. So let T be the transformation. Now, this is just a different notation, guys. This is a new space. This is called a polynomial space. Polynomial space of degree 3. Now, what that means is that this is a space where you only see polynomials of degree 3 or less than degree 3. So that's the cool thing about transformations. Transformations don't only apply to n-dimensional spaces like R2, R3, R4. You can also talk about polynomial spaces where you have this space, and of course, it's not something you can geometrically visualize, but it's a space where you have all the polynomials that have degree less than or equal to 3. So this is the way this goes. The input, right, the domain is a polynomial of degree 3. So what do polynomials of degree 3, less than 3, less than 3. So if you have a polynomial space of degree less than 3, then you're either degree 2, degree 1, or degree 0. And these look like the following: ax squared plus bx plus c, right? These are the polynomials in degree less than 3 space. And this polynomial, when you apply it to this linear transformation, I get a new polynomial. And this is the new polynomial that they give me. 2a plus b x squared plus 5ab, 5a plus 5b plus c, x minus a. Now, the reason why I'm doing this one is because it's a little different from the rest. Now, what are the standard basis vectors of P3? There's no E1, E2, E3 here. The standard basis vectors of P3 is 1, x, and x squared. So in this new space of things, these are the building blocks, right? 1x and x squared. When you have a combination of these, then you have something that looks like this. Do you see the connection? Because I think this is where we just went to a different dimension now with polynomial spaces. And so the idea again is that I can apply the standard basis here. So if I apply t of 1, what does that give me? If I apply t of x, what does that give me? And if I apply t of x squared, what is the result of that? Now, t of 1, I can rewrite this as what? T of 0x squared plus 0 times x plus 1. T of x can be written as 0x squared plus 1 times x plus 0. And this would be t of 1x squared plus 0 times x plus 0. So what matters is what a, b, and c are. Here, this is a, this is b, this is c, this is a, this is b, this is c, this is a, this is b, and this is c. So using these a, b's, and c values for a, b, and c's, I can find what the result would be. So a, b is 0, so this would be 0x squared. A, b is 0, but c is 1, so this is 1x. And this is minus 0, so this just would be x. 1x, right? And then this would be what? 0, this would be x squared plus 5x minus 0. And the last one would be 2x squared plus 10x minus 1. Now, do you see, I don't know if you see this yet, but you can treat this you can treat this like E1. You can treat this like E2. You could treat this like E3. You can treat it like it. You can treat this like a vector here. What would this vector look like? This would look like 0, 1, 0. What would this vector look like? This would look like 0, 5, 1. What would this vector look like? Negative 1, 10, 2. So the coefficients of x squared is like my third element. The coefficients of x is like my second element, and the coefficients of the constant term is like my first element in my vector. And so then what would be the matrix associated with t? It would be 0, 1, 0, 0, 5, 1, and negative 1, 10, 2. And then all you have to do is find what A inverse is, which would be applying the inversion algorithm to find A inverse. Once you find A inverse, then you would find what T inverse would be. I think we went a little bit over time, and we'll continue this on Monday.